Good morning all. So today we are going to discuss the rest of the part what we have left in the previous class. One losses we have discussed, that is called dielectric loss, and we have seen what is the attenuation, how it happens, and what are the factors on which this attenuation depends. So today we are going to discuss two more losses. One is ohmic power loss and one is due to the radiation loss. Last class I have discussed the dielectric loss. Today we will discuss this particular part. Now the thing is that in our microstrip the ohmic is only with respect to the conductor, okay, and due to the metallic plate which is above the substrate, which is a thin plate, due to that some conductivity will be there. In that conductor, either it is made up of aluminum, either it is made up of copper or a good conductor. We are considering copper and aluminum are the good conductor which carries the flow of current, okay. So due to which the losses will be there, some potential drop will be there. When we are providing the external potential to the upper plate, the electric fields are emerging out and it is penetrating through the substrate and enters to the ground plane. So this is the basic analogy. And the magnetic fields flow across the device with respect to the flow of current. If the current is flowing in a particular, suppose let us consider in this particular direction, then magnetic field will come out from a particular page. If it is moving in this particular direction, magnetic field enter into the particular page. So depend upon the direction of current, magnetic field will be identified. And one more important thing, the electric field and magnetic field both are perpendicular to each other. So these are the two characteristics of a particular microstrip line, and depend upon that the relative permittivity and the characteristics impedance are going to be changed. So those changes we have seen for the particular design of microstrip line, and we have seen what are the attenuation factor, what are the factors on which this attenuation depend. One is due to the dielectric substrate and one is due to the conductor. So dielectric substrate we have discussed, that is called alpha D. Now today in this class we are going to discuss about the ohmic losses. So ohmic losses is basically depend upon the surface resistance, okay. Skin depth, how much electric field or magnetic field penetrating to a particular conductive medium. So it is basically a skin depth. So if the skin depth is more, attenuation is less. If the skin depth is less, attenuation factor will be more. So these are inversely proportional to each other. So these are the relations what we are going to see. And this particular factor also hamper with the help of this W by H ratio, because in microstrip we have a aspect ratio, that is width of a conductor, width of a metallic plate, and H is the height of the substrate. If you vary, if your width and H is varying, then your characteristics impedance, your relative permittivity, even your attenuation is going to be hampered. So that we are going to see in today's class. So here I have written all these derivations so that we can cover the syllabus more faster way, because next week your exam is going on, is to be conducted. So here I have written all these equations. I will explain the equations step by step. So first, this is ohmic losses. Ohmic losses means due to the conductor, okay. So here we are discussing more about alpha suffix C. So attenuation due to the conductive medium. Dielectric loss we have seen as alpha suffix D, okay. Now we will deal with alpha suffix C, because this alpha C plus alpha D is equals to the total attenuation suffered by a particular device or a particular microstrip line, okay. So here microstrip conductor contribute the major part of the ohmic losses. Why? Because it is a conductor, some losses will be there, and that losses is called ohmic losses, okay. And that losses it depends upon two cases. One, if W by H ratio is greater than 1, and next if W by H ratio is less than 1, or if it is some other value. So I have jotted down the two particular cases through which we can understand if the W by H ratio is greater than 1, then which particular part we have to consider, and if it is varying, then which particular part we have to consider. So here you can see, if W by H ratio is greater than 1, Okay, then your alpha C is equals to 8.686 divided by Z0 into W into RS. RS means it is a surface resistance. Surface resistance of what? Surface resistance of the thin metallic plate which is above the substrate. Okay, and that RS is basically related with the skin depth. So RS, the surface resistance, we can write root over of pi f mu divided by sigma, and Rs is equals to 1 by del sigma also we can write. Del is nothing but a skin depth which is also inversely proportional to 1 by root over of pi f mu sigma. This all relation we have come across while we are discussing the wave propagation. So the penetration of a particular wave in a particular medium is called as a skin depth, and it is inversely proportional to the attenuation constant. So here you can see alpha C is equals to 8.686. This is the standard value identified by the Pucknell. Pucknell is he was a scientist who has identified this relation, and it gives a brief picture. As you can see, RS is inversely proportional to the skin depth, and attenuation is also inversely proportional to the skin depth, so it satisfies. But for the variation of this aspect ratio, this standard value we have to see. First of all, in that question, while identifying the microstrip line problems, first you have to check whether the width and height ratio is greater than 1 or not. If it is greater than 1, then you have to use this relation. You have to identify the surface resistance. Surface resistance doesn't depend upon this W by H ratio, but the alpha C depends on W by H ratio. So this attenuation depends on surface resistance, characteristics impedance, and the width of the thin metallic plate. Okay, where RS is the surface resistance measured in ohm per square. Okay, and RS is equals to 1 by del sigma, that also we can write, and del is what? It is nothing but the skin depth, centimeter inverse or meter inverse you can write. So it is 1 by root over of pi f mu sigma. So this is the relation if our aspect ratio is greater than 1. Okay, similarly we have second case for the narrow width, means narrow strip line. Narrow strip line means width of the strip line is less with respect to the substrate height. So in that case, W by H ratio is less than 1. This is called as our wider one. Okay, this is called as our wider strip because the W is greater than H. Okay, here it is a narrow strip line. Narrow strip line means the width of the metallic strip is less with respect to the height of the substrate. Okay, so W by H ratio is less than 1. So Pucknell is a scientist who has gone through this equation and satisfied that if there is a variation of W by H ratio less than 1, then what are the conditions are going to be identified. We need not to bother about the derivations. Here only the representation, and only as per the given questions we need to analyze it. We need to use a particular relation for that particular statement. Suppose if we will check W by H ratio is greater than 1, we have to follow this condition. If the W by H ratio is less than 1, then we have to follow this condition. So here Pucknell has given alpha C Z naught H by RS. So here you can see alpha C Z naught RS and W. So here it is H divided by RS. So this is the constant factor with respect to the width. So it is 8.686 divided by 2 pi 1 minus W dash divided by 4H whole square, and the rest of the component 1 plus H by W dash plus H by pi W dash ln of 4 pi W divided by T plus T by omega and T by W. For W by H less than equals to 1 by 2 pi, means more or less. If it is near about 1 by 2 pi, then what will happen? This aspect ratio. So one range is W by H is less than equals to 1 by 2 pi. W by H lies between 1 by 2 pi to 2, and another one is 2 less than equals to W by H. So in these three different cases, our constants will vary. So for this alpha C Z naught H divided by RS, as per this question, W by H, if I will identify, if this value is lies between 1 by 2 pi, because in this equation you see alpha c into z naught, okay, then rs you take in denominator, and w by h, if you multiply numerator and denominator, you will get in terms of h, and the resultant value, if it is less than equals to 2 pi, then your standard value will be this much. Only we have to substitute the given data, okay, width, height, thickness of the substrate, thickness of the strip, width of the strip, this much. So these are the quantities. When we will solve the numerical, then we will see what are the parameters we are going to identify. So these are the certain conditions through which we can analyze the W by H ratio. If it is less than 1 by 2 pi, then this is the condition, okay. Then if W by H ratio is lies between 1 by 2 pi to 2, then my condition will be 8.68 divided by 2 pi. This whole parameter remain as it is, but here in place of this 4 pi W by T, it is nothing but 2H by T minus T by H. So only this much is the difference. So here we are considering 1 plus H by W dash plus H by pi W dash ln of 4 pi W T plus T by W. For this condition, if it is lies between 2 and 1 by 2 pi, this component reduces to ln of 2H by T minus T by H, and rest of the thing remain as it is. You can see here, okay. Next, if W by H ratio is greater than 2, okay, if W by H ratio, if it is greater than 2, then what happens? Then ZC, alpha C Z naught H by RS, which is nothing but W by H, 8.68 divided by W dash by H plus 2 by pi ln of 2 pi E W dash divided by 2H plus 0.94 whole into W dash by H plus this component, and rest of the component remain as it is. So this component remain as it is. So these are the additional factors which are going to be come into picture. It's quite difficult to remember these steps, but you can correlate that what are the missing factors are there. According to that, if you remember this, then rest of the thing will be easy for you. In this and this, it is less than 1 by 2 pi, so here it is ln of 4 pi W by T plus T by W. If it is greater than that, then this ln of it will become as a 2H by T minus T by W. So that is the difference. Similarly, if it is greater, this component remain as it is 8.688, and these are the additional component which is going to be multiplied. So this derivation is not required, only the standardized equation is important for us, okay. And these equations are stated by the Puckle. He is the scientist who has identified all these relations. So according to that, and what are the components are missing? What is alpha C? Alpha C is the attenuation constant due to the conductor. Measure can be decibel per centimeter or decibel per meter. Then here E is there. E is a constant coefficient. It is 2.718, and W dash, you can see W dash is the incremental width due to the potential drop. Suppose in a particular conductor, when the potential drop takes place, it elongates either width wise or length wise. Some elongation will be there. So that elongation is identified by W dash, W plus del W. And what is del W? Del W is again depend upon this W by H ratio. So if it is lies between 2T by H and pi by 2, then del W is T by pi ln of 4 pi W by T plus 1. And if it is greater than pi by 2, then it is T by pi ln of 2H by T plus 1. So these are the component which help us to identify which particular value it is. So these sort of questions may come in exam. Either they will ask in terms of derivation with respect to the certain cases. They will provide if the width of the strip is greater than the thickness of the substrate, then what are the condition? Or they may ask that if the width is less than with respect to the thickness of substrate, then what is the condition for the attenuation constant for the conductive loss? Or you can say it is called ohmic losses. So these are the certain representations which comes regularly while discussing with respect to the aspect ratio. If the aspect ratio changes, these all parameters are going to be changed. and that too you have to see whether these conditions are satisfied or not. Which condition is given? Okay, W by H is less than 1, fine, so we will provide this. But W by H ratio less than 1, but which particular condition? Whether it is W by H is less than equals to 1 by 2 pi, or it is 1 by 2 pi less than 2, or it is greater than 2. So which particular case? So depend upon that your attenuation factor are going to be decided. Okay, so this is the basic derivation for the ohmic losses. Now we will discuss about the radiation loss. Okay, so next one is our radiation loss. Now the thing is, already we have discussed the attenuation due to the conductor, attenuation due to the dielectric. Moreover, the losses may happen with the help of the radiation also. Radiation means whatever the field is emerging out from the conductor, upper conductor, and while it is moving to the air, and then again it is penetrating to the ground plane, which is also a thin conductor, and in between that dielectric is also there. So that radiation, when it is penetrating to the dielectric, the losses may happen. So that is due to the radiations of a electric field or magnetic field. Now, as this Puckle has identified some relation with respect to the attenuation constant for the conductor loss, or we can say it is called ohmic loss. Similarly, one more scientist, that is, his name is called Lewins, he has stated some theory. By considering some approximation, he has derived a particular relation through which we can identify the radiation losses. With the help of this radiation loss, you have to identify the radiation resistance, because whenever this microstrip will come into picture, always we have to deal this microstrip line in a form of an antenna. And antenna, when it is identified with respect to a certain radiation, some radiation losses will be there, and radiation losses is due to the radiation resistance. Okay, our main motive is to identify the radiation resistance and the characteristics impedance of the whole system, okay, by the variation of that aspect ratio and this radiation resistance. These will play a vital role. Okay, now radiation resistance depends according to the approximation of Lewins. He stated that TEM transmission, that means my microstrip line, which is a quasi TEM, his assumption is that it must be TEM transmission. That means at a time electric field and magnetic field both can propagate in a particular direction, and those fields must be perpendicular to each other. Okay. Second assumption is uniform dielectric in the neighborhood of strip equal to the effective value. That means your dielectric value will remain constant throughout the system, means throughout the operation. It may not change. It will not change throughout. It should be uniform. And the relative effective permittivity epsilon Re must be same as the dielectric constant. Okay, so that is, he is saying that uniform dielectric in the neighborhood of strip is equal to the relative effective permittivity. That is the second assumption. Third assumption is neglect of radiation from TE field parallel to the strip. Means whatever the transverse electric field is propagating which is parallel to the strip, we need to neglect it. That means it is neglecting the fringing also. So due to that, these radiations from the TE field parallel to the strip, if we neglect, that means effect of that penetration to the dielectric is minimized. So it will, whatever the radiation will takes place, it is in air medium. We are radiating the electromagnetic wave out of the particular microstrip line. So we are neglecting the surface. Okay, means not surface, neglecting the parallel of a strip. So it will move out. Okay, so it will move out from a particular strip, not in a parallel mode. Next, the substrate thickness must be much less than the free space wavelength. Substrate thickness means your H must be less than the wavelength. Okay, the thickness of the substrate must be less than the wavelength in a particular air medium. So what is lambda naught? Lambda naught is C by F. What is F? F is the operating frequency what we are providing to a microstrip line. Okay, so depend upon this for assumption, he has identified a particular relation, okay, which forms the radiated power with respect to the total dissipated power in a microstrip line. So if I will identify that relation, my theory for identification of this radiation loss will be identified. And this radiation loss basically depends upon two factors. One, substrate thickness, that is called substrate thickness H, and one more important thing, the dielectric constant of that substrate. So these are the two parameters on which this radiation losses will happen. It depends upon these two. One is thickness and one is the dielectric constant. Okay, how? Let's see. So Lewins has stated the radiated power divided by the total dissipated power. Okay, radiated power by the total dissipated power, and he has given it is P rad divided by dissipated power. Okay, so that is equals to 240 pi square H by lambda naught whole square F of epsilon R suffix E divided by Z naught. This is a function which depends upon the relative permittivity. He has identified this relation. Okay, and if you reduce this whole component into R suffix R, this radiation resistance will come into picture. So basically P rad divided by PT is ratio of a radiation resistance with the characteristics impedance of a microstrip line. So this Z naught is also depends upon W by H ratio, and this radiation resistance only depend upon the thickness. Okay, only the thickness of the substrate, that is H. As you can see that R suffix R I have written 240 pi square, means these are the component H by lambda naught whole square into F of epsilon Re. So that means it depends upon dielectric value, relative dielectric value, and the thickness of the substrate. So as you can see, this function F of epsilon Re, here I have written epsilon Re plus 1 divided by epsilon Re minus epsilon Re minus 1 divided by twice root over of epsilon Re root over of epsilon R suffix E whole into ln of root over of epsilon Re plus 1 root over of epsilon Re minus 1. These are the standard functions for the relative permittivity in which the radiation losses is identified. Okay, so here our main motive is what? If the radiation resistance is known, I naught square into Rr, you can identify the losses, power loss, radiation loss. Okay, so once the radiation resistance is identified, it is easy to identify the loss. What is the power dissipation? The power dissipation with respect to the radiated power, this is the relation what he has given, and this relation indicates that whatever the radiation losses will happen, it is only due to the two factors. One is dielectric constant and one is the thickness of the substrate. Thickness of the substrate means H, dielectric constant means epsilon, dielectric constant of the dielectric medium epsilon D, and the relative dielectric constant, that is epsilon Re. So these are the two factors due to which this radiation will happen, radiation losses will happen. Okay, due to which we can identify the radiation resistance, because whenever we will use this microstrip line as an antenna, microstrip antenna, in that case we will see how this radiation resistance will come into picture. This radiation resistance will help us to identify whether we are using the half wave dipole, whether we are using quarter wave dipole, whether we are using microstrip line, which sort of parameters we are using, which sort of devices we are using. According to that, the radiation resistance will change. So here we are using the microstrip line. So radiation resistance will have 240 pi square H by lambda naught whole square F of epsilon Re. So that means the radiation resistance depend upon what? It depends upon substrate thickness, it depends upon the dielectric of the substrate, it depends upon the net dielectric, that is the relative effective dielectric value of a particular system. So if we know all these relations, then it is quite easy to understand. Okay, and what is our epsilon Re? Epsilon Re is equals to 0.47 times of epsilon R plus 0.61. So like this, some relations is there that we will see while solving the numericals. So your epsilon R, if it is given, relative permittivity is given, you can identify the relative effective permittivity. Okay, that I will give the relations. So for the timing, so this is the particular relations through which we can understand the radiation resistance, and once the radiation resistance is known, we can easily identify the losses. How? Power loss is how? I naught square into R suffix R. So this is the basic relation through which we can identify the radiation losses, attenuation losses. There are two types of attenuation loss. What is that? One is the dielectric loss, one is the ohmic loss, and one more important loss is what? One more important loss is the radiation loss. So these are the certain relations which help us to understand that these are the certain losses may happen when we are using the microstrip lines for a radiator or acceptor. Means either it can radiate the signal or either it can receive the signal. Okay, electromagnetic energy will penetrate on that conductor. It is converted into potential and current, and we can extract our information while receiving. While transmitting, what happens? Potential and current is given to that system. It is converted into electric field and magnetic field. Okay, so this is the basic relations. Next we will see on what particular basis this device is measured. All the devices are measured on a particular performance value, that is called quality factor, and this quality factor will judge what sort of losses, and if the losses happens, what will happen to the quality factor, how we can upgrade the quality factor, what are the parameters are there, that we will discuss now. Okay, so quality factor for the microstrip line. Now in microstrip line we have two things. One is thin conductive plate which is upper the substrate. One is the dielectric substrate having a thickness h with the dielectric value epsilon. Okay, and the ground plane which is also a thin conductive plate. So basically we bother about the upper metallic plate and the substrate, what it is in between that upper and the lower metallic plates. Okay, so the quality factor will be judged according to these two things. One, with respect to the conductor, whether it is a wider, whether it is a narrow, depends upon that W by H ratio, and one more important thing with respect to the dielectric. So two quality factors you have to identify, one with respect to the conductor, one with respect to the dielectric value. Okay, so let's see. So here the microwave integrated circuits, whatever the circuits we are using for communication purpose, that is called MIC, microwave integrated circuit, whose quality factor must be very very high. That means the resonating power for a particular circuit must be very very high. So quality factor must be very very high. So Q factor must be very very high. So now when we are dealing with the microstrip line, we have two attenuation constants. One with respect to conductor and one with respect to dielectric value. Always remember that your quality factor depends upon this attenuation factor. Quality factor will high when the attenuation factor is less. Quality factor will be low when the attenuation factor is high. So we have to always minimize the attenuation so that the circuit can properly work in a resonating condition for a higher output. Okay, for a higher measurable output. So for that I have used for the conductive, I have started with alpha C, and then we will discuss how it is related with respect to the quality factor. Now as we know that W by H ratio, here I am considering W by H is greater than 1. Okay, if W by H ratio is greater than 1, then alpha C is equals to 8.686 into RS divided by Z0 into W. What is RS? RS is the surface resistance. What is W? W is the width of the metallic strip. And what is Z0? Z0 is the characteristic impedance of that medium. And what is Z0? Z0 is equals to H by W root over of mu by epsilon, which you can write this mu as mu naught into mu r divided by epsilon into epsilon r. Mu r is air medium, so only epsilon r value will be there, and this root over of mu naught by epsilon naught is called as a 377, or you can write 120 pi. So it is 377 divided by root over of mu epsilon r. Here mu value is mu r into mu naught. Epsilon is equals to epsilon r into epsilon naught. In this case mu r is 1, so we have mu naught divided by epsilon r into epsilon naught root over. So mu naught by epsilon naught, your value is 120 pi. and remaining is 1 by root over of epsilon r, and that 120 pi value is 377, okay, multiplied value. So into h by w. So this is my characteristics impedance. Over. Now when it is wave is propagating through a particular microstrip line, means it is a guided wave. Okay, so your wavelength will become as a guided wavelength. So guided wavelength is 30 divided by f root over of epsilon r. Here I have measured in terms of centimeter. So here I have written 30. So 3 into 10 to the power 8 divided by f root over of epsilon r, that also you can write. Here directly I have written the value. And what is our quality factor with respect to the conductor? As I have told, your quality factor will be inversely proportional to the attenuation factor. So attenuation factor with respect to the conductor, that is called alpha c. So it is 27.3 divided by alpha c. So you have to see what is the alpha. One more important thing, in a question when it is given W by H ratio greater than 1, that means you have to use this alpha c. But if it is not, if it is less than 1, then as I have discussed with the ohmic losses case 2, according to that you have to select your alpha c, and then you have to proceed with respect to the determination of quality factor. So this quality factor is 27.3 divided by alpha c. So this is the quality factor can be measured with respect to the guided wavelength. Here we have identified alpha c. This is decibel per meter, but since this attenuation constant is within a particular waveguide, you have to divide with lambda g. So your unit will be decibel per lambda g. So whatever the lambda alpha c you have got, you need to divide with respect to lambda g because it is within a waveguide, and then you can determine the quality factor, that is 27.3, and substitute the value of alpha c. Don't directly substitute this value because this quality factor we are going to identify for the whole system, so it is within a waveguide. So your guided wavelength need to be divided. So here I have written the unit dB per guided wavelength. So whatever the lambda you are getting here, you need alpha, you have to divide this alpha c divided by lambda g and substitute in this equation. That is 27.3 divided by alpha c. So this is the quality factor with respect to the conductor, upper conductor, metallic plate. Now we will see for the wider strip what will happen. Means W by H ratio is greater than 1. So we have used this alpha c. Okay. And this QC can be minimized as 39.5 whole into H by RS into F, because operating frequency plays a vital role. Surface resistance plays a vital role. So after substituting all these things, 39.5 whole into H by RS into F, which is in gigahertz, where H is measured in centimeter, RS is the surface resistance, and which is measured with ohm per squares. Similarly, this can also be disseminated, as 0.63 H root over of sigma into F. Root over of sigma into F means if sigma value is given, you can directly substitute here. Either the sigma value will be conductor for copper, for aluminium, whatever the good conductor is given, substitute the value here. You can directly identify the quality factor for the wider strip. Similarly, for the copper strip, if I am using, simply I will substitute the sigma c here and operating frequency, multiply it, and you will get Q suffix copper is equals to 4780H root over of F. That means this whole value I have substituted in this, took a square root and multiplied with 0.63. I got 4780H root over of F, which is in gigahertz. So the value will be given to you, only you have to substitute this value. Next, the quality factor we have to identify with respect to the dielectric. So dielectric loss also we have seen, that is called alpha D. So here quality factor what will happen? It is 27.3 divided by alpha D. Here the changes is what? In place of alpha C, you have to substitute alpha D. And that to be with respect to the guided wavelength. So here I have written lambda naught divided by root over of epsilon Re into tan theta, or you can say it is near about 1 by tan theta. So quality factor for the dielectric medium depends upon the loss tangent angle. So that is tan theta is equals to sigma by omega epsilon. This sigma is the dielectric conductivity, remember that, and omega is the angular frequency and epsilon is the dielectric value, substrate dielectric value. So this value, if you substitute here, you will get the quality factor for the dielectric. Okay, so these are the quality factors for the conductor as well as for dielectric medium, because we are discussing for a microstrip line, which is a combination of a metallic conductor with a substrate and with a ground plane. Okay, next we will discuss the different lines are there, what are the parameters. Okay, so next one, so microstrip line, the parameters we have identified. Next we are going to discuss about the parallel lines. Okay, because this is also one sort of transmission line which helps to transmit the signals. Okay, these are called parallel plate. Already we have discussed how to determine the RLGC parameter for the parallel lines. Same thing we are going to discuss here, but here the dielectric value we have to represent with respect to epsilon d and the mu d for a particular medium. As you can see in this figure, there are two parallel plates are available, separated at a certain distance d. So d is the distance and the width is w. So here the aspect ratio will depend upon w and d. Okay, so here aspect ratio will be w by d. In microstrip line it is w by h ratio, remember that. In microstrip line we are identifying with epsilon re, relative effective permittivity for a particular medium. Similarly here we are identifying with respect to the dielectric, so it is epsilon rd we have to use. So for parallel line epsilon rd we have to use, and for strip line we have to use epsilon re, relative effective permittivity for microstrip line, relative dielectric permittivity for the parallel lines. So this is the two difference, but the working principle will be same. So this already we have identified the parameters when we are discussing the transmission line, what will be the RLGC parameter for the parallel lines. Same thing I am not deriving all those things, but I am assigning the particular factor to it. So what are the factors? Let's see. Okay, so this is the two parallel plates which is separated at a distance d. Dielectric medium is epsilon d and mu d is represented. Okay, epsilon d and mu d is the medium for the dielectric substrate, and the width of the plate is w, separated at a distance d. So what will be our aspect ratio? Aspect ratio will be w by d. So this is my aspect ratio. So due to the variation of this aspect ratio, my all parameter will change. Okay, let's see. So here there are three basic things we have to identify first. One, width of the strip, that is w. Second, the separation of the strip, that is small d. And third, the relative dielectric constant, that is epsilon rd. So these are the three basic components while designing the parallel plate lines or parallel strip lines, you can say. Now as we can see in our medium, depend upon the medium we can judge whether which type of line it is. So if it is a lossy line, what will happen? If it is a lossless line, what will happen? Basically there are four distributed parameters. Here I am going to discuss about the distributed parameter of a line, that is called four parameters R, L, G and C. So already this RLGC parameter we have found out for the parallel lines. Here only we need to assign it with respect to W and D and with respect to alpha suffix RD. Okay. So for lossless line, only the L and C value is going to be identified. R and G both are 0. But if it is not lossless, what will be its general equation? Your R will be exist, L will exist, C will exist, even G is also going to exist, and all are measured in terms of per unit length. Okay. Next, since it is a transmission line, parallel lines, it operate in a quasi-TEM mode. Since it is satisfy the working principle of transmission line, because transmission line operate at a TEM mode, similar to the microstrip line, this parallel strip line is also working in a quasi-TEM mode. Okay. And let us consider the wave is propagating in this particular direction along z axis. along z-axis. So your electric field and magnetic field will either move along x-axis or y-axis perpendicular to each other, and it is guided by within a strip line, two strip line. Next, if W by D, if the width is greater than this separation, then it is called wider strip line. Okay, wider strip line, and that too the fringing capacitance is neglected. This is the most important factor. Remember this. In microstrip line we are considering the fringing effect. Okay, but in parallel line, in parallel strip line, if the width of the strip line is greater than this separation, we need to neglect the fringing effect, because all the electric fields and magnetic field is within the parallel plate. Okay. Next, so here we are going to identify our RLGC parameter. As you can see, L we have already identified, which depends upon mu into D divided by W. So W is the width of the strip, D is the separation between the strip, and mu suffix C is the permeability of the conductor. So here mu C is the permeability of a conductor. So L is equals to mu C D divided by W Henry per meter. Similarly, capacitance per unit length we can measure by C is equals to epsilon D into W divided by D. Basically, capacitance formula is C is equals to alpha naught A by D. Okay, but here it is within the dielectric medium, alpha naught is replaced by alpha D, and the cross section, that length I have divided here, and W. So this C by L is capital C alpha epsilon D W by small d. So that I have written directly here. It is in farad per meter. Okay. Now L and C is known. Then what is the value of R and G? R is equals to the resistance for both the strips, so it is twice Rs by W. Okay. If it is only one strip, it is Rs by W. So here it is Rs by W. Why? Because surface resistance of a strip divided by the width for one strip. Here two strips are there, so 2 we have to multiply. So 2 into Rs by W per unit length. Rs unit is ohm, width unit is meter, so it is ohm per meter. So it is twice Rs by W. In place of Rs, you can substitute the surface resistance value, that is pi f mu divided by sigma. So that you can substitute here, and we can form a relation 2 by W root over of pi f mu c divided by sigma c ohm per meter. Similarly, the lumped parameter, which is conductance G, in place of, this is mu d, in place of epsilon d, you need to substitute mu d, sigma d. So if it is sigma d into W by d, you will get your conductance value, conductance per unit length, or Siemens per meter, or mho per meter. So these are the RLGC parameter for the parallel line. So these are the distributive parameter, distributive RLGC parameter for a strip line, and with the help of that you can identify the parameters for a certain transmission line. What are the parameters? Characteristics impedance, velocity, attenuation constant, then what is the phase constant, and what is the guided wavelength. All those parameters can be identified. So here what I have done, here it is G is equals to sigma d by W by d. So sigma d is the conductivity of the substrate, that you have to remember. Here it is alpha epsilon d, it is the dielectric value of the substrate. Sigma d is the dielectric conductivity of that substrate, and d is the separation, width is, W is the width of the strip. Okay, so G is the conductance per unit length. Next, if it is a lossy or lossless, both the value will be same for the parallel strip line. Okay, so Z0 is equals to root over of L by C. In place of L, whatever the value we have, that is mu C d by omega W, and what is C? Epsilon d W by d. Substitute here, you will get d by W root over of mu d by epsilon d. In place of mu d and epsilon d, we can substitute mu 0 into 1 divided by epsilon 0 into epsilon RD, relative permittivity. So if you take mu naught and epsilon naught root over, you will get 377. We have left with epsilon RD that I have substituted here. So 377 divided by root over of epsilon RD whole into d by W, and W is very greater than D. Why? Because it should satisfy that quality factor also, for high quality factor. So Z0 is equals to this much characteristics impedance. Similarly, your phase velocity we can identify C by epsilon RD. C is what? C is nothing but the speed of light, okay, divided by epsilon RD. So basically the phase velocity we are identifying as 1 by root over of LC. So whatever the value of L and C are there, you can substitute here, and mu C into epsilon D that we will get. In place of mu C you can substitute mu naught into 1, and in place of epsilon D you can substitute epsilon naught into epsilon RD, so whose value is Vp whole into equals to C by root over of epsilon RD. So here in place of this I can write mu C into epsilon D, which is nothing but mu naught epsilon RD, which is equals to C divided by epsilon RD that I have written. Okay. So velocity also you can determine, even your phase constant also you can determine, omega by beta is equals to 2 pi by lambda also you can determine, lambda g you can determine. So all those parameters can be easily found out. Okay. So this is the characteristics impedance, and these are the lumped parameter for a strip line. And one more important thing, we have to identify the loss. What is that loss? This is called as a attenuation loss. What, as we have seen, the microstrip line attenuation loss depend upon, one is conductive loss, that is ohmic loss, and one is dielectric loss, alpha C and alpha D. Similarly, our parallel line is having certain losses that is due to the attenuation that we will see now. Okay, so in parallel strip line also we'll have the attenuation loss. In parallel strip line also we have two variety of dielectric medium. One is the conducting plate, upper plate and lower plate, and in between that substrate is available. Okay, so that substrate is having a dielectric value alpha epsilon D, and the permeability is mu D. Similarly, so here also we are going to identify the two attenuation factor which help reduce the information due to the certain losses. Now, as we have seen in our microstrip line, we have identified alpha C, we have identified alpha D separately as ohmic loss and the dielectric loss. So here also we are going to identify the attenuation factor. Then after the attenuation factor, if you convert that Nepper per meter into the decibel, you are going to identify the losses. Okay, and 1 Nepper is equals to 8.686 decibel. What is the relation we have seen? So same thing we are going to implement here also, but according to the lumped parameter. Okay, so as you can see here, the main important factor is our propagation constant, because this propagation constant, if the real factor exists, that means gamma value, as we can say, it is alpha plus j beta. It is a complex value. Its unit does not have any constant, does not have any sort of unit. So propagation constant, if the real factor exists, that means attenuation will be there. And if the attenuation is there, attenuation losses will occur. Okay. So this relation already we have seen in our transmission lines, that is gamma is equals to R plus j omega L whole into G plus j omega C. Now if it is such conditions, condition is R is less than equals to omega L and G is less than equals to omega C, means lossy condition. Okay. Now if you take this R and G as a common to certain imaginary parts separate and the real parts separate, then we have the real part is half of R root over of C by L plus G root over of L by C plus j omega root over of LC. So if I will compare this equation, this alpha value is nothing but this, and j omega root over of LC the value of beta. So that I have written alpha is equals to 1 plus R root over of C by L plus G root over of L by C, and beta is equals to omega root over of LC. And lambda easily you can determine, Lambda is equals to 2 pi by beta. Whatever the beta value is there, you can identify that. And phase velocity is equals to omega by beta. That also you can substitute here. And we can identify the phase velocity. Okay. Next, this alpha is having two components. One is alpha C, one is alpha D. As I have told that your strip lines is a combination of a dielectric medium and the conductive medium. So your attenuation factor depends upon conductor and the dielectric. So conductor means the resistive value we have to consider, and the dielectric means conductance value we have to consider, because in conductance we have seen that G is equals to sigma D D by W, like this. So this relation we have identified in the previous discussion. So here you can see sigma D is depend upon the conductance, okay, so of a dielectric medium. So from this equation, if the resistive value you are taking it as separate, it will identify as a conductive loss, and this conductance with the root over of GLC is indicated as a dielectric loss. So here I have represented alpha C is equals to 1 by 2 R root over of L by C, and alpha D is equals to half G root over of L by C. This is C by L, this is L by C. Again, if you disseminate 1 by D root over of pi F epsilon D by sigma C, and this one you will get 188 sigma D divided by epsilon RD. These all are in Nepper per meter. Now you can convert this Nepper per meter into decibel so that you can identify the attenuation loss. What is the loss? One is conduction loss, one is the dielectric loss. So this Nepper per meter, if you convert into decibel per meter, if this is also decibel per meter, then this is called as a ohmic losses. This is called ohmic loss, and this is called dielectric loss. So these are the two losses which we are going to face while using the microstrip parallel lines, or sorry, it is a parallel strip lines, or when we are discussing with respect to microstrip lines. Apart from these two lines, we have two more lines. Only we have to identify the characteristics impedance and the nature of the working principle of those lines, and it will help us to understand what are the factors behind those particular lines and how to identify that particular working principle, how it works, that matters. Okay. So next class we are going to discuss two more strip lines. Okay, one is coplanar line and one is sealed line, and few numericals regarding the discussion what we have done for microstrip line, for parallel line, for the coplanar line and the shielded line. So we will solve few numericals which are very important for your internals as well as for your external exams. And this thing we will discuss in the next class. For the time being, we will end up here because already time is over, and we will discuss the rest of the part of the third module in the next class. Thank you all.